So today, we're going to break down the Carnot cycle into simple terms. Now, the Carnot cycle is a theoretical model that represents the most efficient heat engine possible. But it's important to remember that the Carnot engine is an idealization. In other words, this type of engine sets an upper limit to the efficiency of any heat engine working between the temperature of the hot and cold reservoir. And I'll explain this in more detail in a minute. No real engines can be more efficient than the Carnot engine. But the Carnot engine is useful because its thermodynamic cycle gives us a benchmark to improve real-world engines, power plants and refrigerators. So what we have here is a PV diagram of the Carnot cycle and a visual schematic showing a piston undergoing 4 distinct stages. And I'm going to talk you through each thermodynamic process. When we go from state 1 to state 2, the gas in the chamber is expanding isothermally, and this is while heat flows into the system from the hot reservoir. When a gas expands isothermally, its temperature remains constant, and we can see this here on the PV diagram, as our process does not deviate from the isotherm T sub H. We can also see that the gas absorbs heat Q sub H during this transition, and positive work is being done by the piston. From state 2 to state 3, the hot reservoir is removed, so now no heat is entering the system, but the gas continues to expand. And because the system doesn't have heat flowing into or out of it, this expansion is adiabatic. But also notice that the gas in the chamber is still doing work on the outside environment. So if we write down the first law of thermodynamics, we can see that the change in internal energy of this gas here within this chamber is equal to negative work. And this is because in the adiabatic process, the heat exchange is equal to 0. This means that the gas's internal energy is dropping during this adiabatic expansion, and therefore its temperature also decreases. If we look at our PV diagram, we can see that state 3 is located at a lower temperature isotherm, T sub C, than state 2. The temperature has fallen during this process. We now place our chamber in thermal contact with a cold reservoir, which allows heat from the gas to flow out into this cold reservoir. This compresses the gas isothermally at temperature T sub C, which we can also see on the PV diagram here. And also notice that the gas expels energy Q sub C, which we've labelled on the PV diagram as well. Because the gas is shrinking in volume, the work done by the gas is also negative. In the final process, from state 4 to state 1, we remove the chamber from the cold reservoir so that the gas in the chamber is thermally isolated. But from state 4 to state 1, the gas compresses adiabatically and therefore increases its temperature back up to the higher temperature isotherm, T sub H. And again, during this process, negative work is being done by the piston. But the total work done by the cycle is equal to the area enclosed by all 4 processes here. Now, if we want to calculate the efficiency of this Carnot cycle, we'd use this equation, where E sub C represents the efficiency of the Carnot engine, and this is equal to 1 minus the difference in temperature between the cold reservoir and the hot reservoir. So this equation basically shows us that the efficiency of a Carnot cycle depends only on the temperature difference between the hot and cold reservoir, and no real heat engine could have a greater efficiency than the Carnot efficiency. We should also notice here that an efficiency of unity or 100% can never be achieved by a Carnot engine. If we could achieve 100% efficiency, the cold reservoir would have to have a temperature of 0 Kelvin. Because if you notice here, if T sub Z is 0, then effectively on the right hand of the equation, we would have 1 minus 0. But you probably already realised that we can't have a temperature of 0 Kelvin. Nothing can reach this temperature. And therefore, the Carnot efficiency can never reach 100%. Now, in most practical cases, the temperature of the cold reservoir is going to be around room temperature, or around 300 Kelvin. So if we want to increase the efficiency of our heat engine, we would need to raise the temperature of the hot reservoir as much as possible. So let's put this equation to use and calculate the highest theoretical efficiency of a steam engine. So let's imagine we have a steam engine that has a boiler that operates at 520 Kelvin. The energy from the burning fuel changes water to steam, and this steam drives a piston. The cold reservoir's temperature is that of the outside air at 285 Kelvin. What is the maximum thermal efficiency of this steam engine? Well, let's use this formula here that calculates the Carnot efficiency, where we have 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. Now, the temperature of the cold reservoir is that of the outside atmosphere at 285 Kelvin, and the hot reservoir is the temperature of the boiler at 520 Kelvin. So when we plug in our values, we get an answer of 0.452 to 3 significant figures. In other words, 45.2%. And this is the maximum theoretical efficiency of this type of boiler operating at these two temperatures. But because this is the maximum theoretical efficiency, we can expect a real steam engine's efficiency to be much lower than this. According to Carnot, it would be impossible for this steam engine to operate at a higher efficiency than 45.2%. So what you should take away from this lesson is this: no real heat engine operating between two energy reservoirs can be more efficient than a Carnot engine operating between the same two reservoirs. And this is Carnot's theorem.